Hello everybody, this is Dr. Christopher White and welcome back for part 2 of Deformation. And before we get started, you know what, let's do the code word right now. Let's get it out of the way. So the code word for today is apple, like the fruit. A-P-P-L-E, apple. Alright, so now let's move on to the types of differential stress. So remember, there are 3 types of differential stress: compression, tension, shear. Tension, if you remember, can also be called extension. So when we're in the brittle regime, so that's the upper 10 kilometers of the Earth's crust, what's going to happen when we expose a rock to compression, tension and shear? Alright, so if we expose a rock which is going to behave in a brittle fashion to a compressional stress, well, obviously, once we squish that layer of rock enough, it is going to fail in a brittle fashion. It's going to crack. And so when that cracks, what's going to happen is we're eventually going to fracture our rock, and the pieces of rock are eventually going to slide past each other. This is referred to as slip. So by compressing our rock, we are going to cause our rock to break, and eventually that compression is going to cause pieces of the rock to start moving past each other, which is referred to as slip. This feature here, by the way, the plane along which slip is happening, is referred to as a fault, and we're going to discuss more about those in a bit. Now, if we expose our rock to tension, what's going to happen? Well, what's going to happen is we're going to have our piece of rock and we're going to stretch it and stretch it and stretch it, but our piece of rock isn't going to do anything because remember, it's solid, it's cold, it's not going to break. We're going to keep stretching it, and eventually it's going to split into 2 pieces. It's going to crack. So we're going to end up with a fracture again. Now, depending on what happens, these 2 pieces of rock can simply just move apart and they will not move relative to each other. If they move apart, then you're going to have a little space in between, and that space is referred to as a joint, and typically that joint will later be filled by some kind of mineral, something like quartz or calcite, and that will fill the space that's opened up. Because remember, in nature, nature doesn't like spaces. Spaces have to be filled with something. And so when you pull 2 pieces of rock apart, you leave a void. That void will eventually be filled by a mineral at some point. Now, the other thing that could happen, though, is if we have our 2 pieces of rock, we've pulled them apart, well, in that case, our pieces of rock could start moving relative to each other, couldn't they? In that case, we've fractured our rock and we have slip again. So sometimes when we expose our rock to tension and we cause our rock to fracture, that can also lead to slip and the formation of these faults. So in this case, this block of rock, for instance, might drop down relative to this block of rock, and that would make this plane here, the plane between the 2 of them, the fault plane. And then finally we can expose our rock to shear. And if we expose our rock to shear, well, for a long period of time our rock's going to be absolutely fine, and then you'll never guess what happens to it. It'll fracture. Yeah. If we expose our rock to enough shear force, it will finally fracture. And then what will happen is the pieces of rock will move relative to each other. So this piece of rock here will slip relative to this piece of rock here, which means, once again, what we have ourselves here is a fault. So if you haven't guessed by now, a fault is simply a plane along which 2 pieces of rock move relative to each other. Alright, so that means when it comes down to it, brittle deformation will result in our rock fracturing, and if conditions are correct, it will also cause pieces of rock to move relative to each other. Now that process of moving relative to each other is referred to as slip. Okay, so if we look at this diagram here, it's going to kind of demonstrate to a certain degree how brittle deformation functions. So this block up here is our original block, and it's 50 centimeters long. And so what we're going to do is we're going to put our block under certain stresses. So in this case, we're going to put our block under a tensional stress and a compressional stress. And our block is going to fail along these red lines. Okay, so let's see, how does our block fail when we expose it to a tensional stress? We're extending it. Well, what's going to happen is our block is going to fail along the red lines, and this piece of the block here is going to move left. This piece of the block here is going to move right. Well, what does that mean? Well, that means as this block moves left and this block moves right, we're going to end up with an empty space, aren't we? So there's going to be a space here between this block and this block, and there's going to be a space formed here between this block and this block. And so the only thing that can be done is for this block in the middle to drop down. And so that's how we accommodate the tension. So what we've done by doing this is by moving this block to the left, this block to the right, and letting this block drop down, what we've done is we've accommodated the tension, the extension of the rock, and now all of a sudden our layer of rock, which was 50 centimeters, is now 60 centimeters. And so all we've done is we've done this by making our rock crack and then having one piece of rock drop down relative to the other two. Done. Simple. Now in a compressional regime, on the other hand, this block here is going to move towards the center. This block here is going to move towards the center. They're going to be pushed towards each other. And that means the block in the middle is going to be pushed up. So what's going to happen there? Well, obviously, by allowing this block to move towards the middle, and this block to move towards the middle and pushing this block up, what we've done is we've essentially decreased the length. So the length of that was originally 50 centimeters, has now decreased to 40 centimeters. And once again, that's been accommodated by, first of all, allowing our rock to crack, so fail in a brittle fashion, and then allowing the pieces of rock to move relative to each other. They've slipped. And the same thing will happen with shear forces. So this is our piece of rock. Now what we're doing is we're looking at this top down. So our piece of rock is 30 centimeters wide and 20 centimeters deep. What we're going to do is we're going to shear it. This half is going to want to go north. This half is going to want to go south. And so we're going to do that. And of course it's going to fail along this brittle plane here. So the rock's going to crack here. This block of rock is going to go this way. This block of rock is going to go this way. And so by doing this, what we've done is we haven't increased the width, because the width is still 30 centimeters, but we've increased the depth. It's now 30 centimeters as well. So what you can see is this process of cracking the rock and essentially letting bits of rock move relative to each other is a method by which we can accommodate compression, tension, and shear. So it allows us to accommodate these forces by simply breaking the rock into pieces and moving those pieces relative to each other. So, pretty cool. And of course, I'm sure you guys have all managed to work this out by now. But obviously, breaking a piece of rock is not an easy thing to do. So in order to make that happen, you need to apply substantial amounts of stress. And so the only force that's really going to be able to do this are tectonic forces. So we're thinking about convergent, divergent, and transform plate boundaries. Okay. So what happens if we apply compressional, tensional, and shear stresses in a ductile setting? Alright, so if we are in the ductile zone, so that's typically about deeper than 10 to 15 kilometers down, what's going to happen to our rock? Well, remember, our rock isn't going to behave in a brittle fashion in this zone. It's going to behave in a ductile fashion, so it's going to flow, it's going to flex. Alright, so if we compress our piece of rock, what's going to happen to it? Well, it's going to fold. So if I have my piece of rock here, this is my piece of rock, and I squish it from the sides, it folds. It's quite simple. Very, very simple. So compressional forces will make rock fold. Okay, what about tensional forces? Well, one of the problems is that it's very, very difficult to stretch something when you are 10 to 15 kilometers down in the crust. You can't really make it work. The rock around you essentially really makes it very difficult to stretch. And so tensional forces are very difficult to accommodate that deep in the crust. But if they do manage to form, what will happen is material in the what will happen is you'll see crystals in the rock will start to get stretched out, and they will crack, as you can see in in this instance they've used rocks, but this would also happen to crystals. You'll see these cracks, and those cracks will get filled in by fluid very, very quickly, and minerals will precipitate in those cracks. The final thing that will happen is shear. So shear will, once again, we're dealing with material now that will flex, and so instead of breaking in a brittle fashion, this side of the block will move relative to this side of the block, and the movement in the middle will be accommodated by flexure instead of brittle failure. So, okay, you can see the rocks are going to behave in a completely different fashion when they're in the brittle zone compared to the ductile zone. Okay, so the next thing to think about is what are the factors which will influence how a rock deforms and the strength of that rock? Well, there are 4 things which are going to affect the ductility and the strength of our rock. Now, before we start talking about them, let's just define what we mean by strength and ductility. So strength is the ability of a material to resist a deforming force. So the ability of a material essentially to resist, either brittle failure or ductile failure. And ductility is described as the ability of a material to be deformed without breaking. So something like silly putty has quite a decent ductility. You can stretch it for a really, really, really long way before it actually fails. Okay, so something of a high ductility can be deformed, but it will not fail. It will not break. Okay, so let's think about the first variable, which is, of course, temperature. So if you increase the temperature, 2 things happen. Number 1, ductility increases. Now, that's not a huge shock to anybody, is it? When you warm up materials, they become more malleable. Also, strength decreases. Well, obviously, because you're heating something up, we know once again the material becomes more malleable. And a more malleable material has essentially 2 features to it. Number 1, lower strength than the original material. And number 2, higher ductility. You can bend it, you can stretch it out. Okay, that's why blacksmiths have to heat up metal before they can turn it into stuff. So increasing temperature, that's not really a huge shock. So essentially the hotter your rock is, the higher the ductility, the lower the strength. Now the next thing we need to think about is confining pressure. Now, as we increase the confining pressure, 2 things happen. Number 1, ductility increases, and number 2, strength increases. Now that kind of seems a bit counterintuitive, doesn't it? But let's try and think this one through. Okay, so let's start with ductility. So remember, ductility is the ability of material to be deformed without breaking. Well, in the case of confining pressure, you can begin to deform the material, but remember, because the material's under lots and lots of pressure, the bonds between the atoms in your material are quite robust. So even if you do start to make your material start to deform, it's not going to break easily because it's so, then we come on to option number 2, strong. Because the atoms are pushed closer together, the bonds become stronger, and so the material actually becomes more and more difficult to break. Now you can begin to make it deform, so you can make it flex if you put enough force on it. But it really, really, really is very, very difficult to make it break. And this bit of experimental work here kind of shows that quite nicely. So what we have here is we have 4 pieces of marble. Now this is what the original column of marble looked like before it was put into what's called a press. And a press is essentially when you squish the piece of rock from top and bottom, and you're applying thousands of pounds of pressure to this piece of rock. Huge amounts of pressure. So what happens? Well, obviously if your rock is in a low confining pressure environment, well, the forces eventually squish the piece of rock and it fails in a brittle fashion. Okay, it cracks. But you'll notice as the confining pressure gets intermediate and then eventually high, you will see that even when it's exposed to extremely high pressures, sufficient pressure to make the rock begin to deform in a ductile fashion, so it begins to warp outwards, it doesn't crack. so it resists brittle failure. So obviously you can see the ductility is increasing, isn't it? The ability, so it's resisting breakage because it's got a higher confining pressure. So ductility is going up, and the ductility is going up because the strength of the material is also increasing. So the material becomes stronger, and at the same time it also becomes more ductile. Okay, part C, the type of rock. Well, obviously that's not really a huge shock. Some rocks are naturally quite weak, and some rocks are naturally quite strong. Some rocks are naturally quite flexible, and some rocks are naturally quite rigid. So depending on the type of rock you have, some rocks will be quite will move in a very, will have a quite high ductility, some rocks will have a low ductility, some rocks will have a high strength, some rocks will have a low strength. That's not really a huge shock. And then finally we have the rate of deformation. So the higher the rate of deformation, the lower the ductility and the lower the strength. So that means if you do something slowly, your material has time to accommodate it. So it doesn't break and it doesn't break. So the classic example of this is, of course, the famous example of the IKEA chest of drawers over carpet. So I think it's pretty likely that nearly everyone watching this video at some point has had to move an IKEA chest of drawers over a carpet. And there's been that point where, you and maybe someone else, you're very slowly pushing that IKEA chest of drawers over the carpet. Everything is going fine. Now, because you're pushing it nice and slowly, your rate of deformation is relatively low. It means what you're pushing is able to accommodate the movement, so it doesn't fall to pieces, so it doesn't start flexing, and it doesn't start breaking. And you think to yourself, okay, good. And then there's that terrible moment when you suddenly get overconfident. And you suddenly think to yourself, right, I can go a bit faster. And then all of a sudden, what do? You start pushing that chest of drawers a little bit faster. All of a sudden, it starts to flex. And then all of a sudden, you hear that terrible crack as a piece of the chipboard somewhere goes and fails on you. So that's what happens when you increase the rate. When you increase the rate, because you're pushing it too quickly now, the material does not have time to accommodate the force, and so its ductility drops, so it can break more easily, and its strength also decreases. So if you want to deform something at a very high rate, essentially it's going to cause your material is going to be more likely to break. Okay, so these are the 4 variables which essentially will affect the strength of your rock. Okay, so obviously depending on whether you're in the brittle or ductile zone, your rock will fail in a brittle fashion or it will fail in a ductile fashion. Well, that leads to 2 main groups of features produced by this process. In the case of ductile deformation, the most common feature is, of course, what we can see here. It's the fold. Essentially, your rock doesn't break, but it forms these arches and troughs. The other feature is a fault, and this is a brittle feature. So in the case of the brittle feature, you can see the rock has cracked along this plane here, which is called the fault plane, and the blocks have moved relative to each other. So you can see in this instance, this block here has dropped down relative to this block over here. So ductile deformation, brittle deformation. Okay, so let's think about faults. So folds are produced by a layer of rock bending under stress. So in order to form a fold, most of the time your stress must be compressional. So you are typically going to find folds formed at convergent plate boundaries. Now, when you try and fold something, it might seem a little counterintuitive, but in order to fold something, you need to fold the strongest layer first. So imagine you have yourself a sequence of pieces of foam, okay? And in the middle of all those pieces of foam, you stick yourself a sheet of steel. Now, if you try and compress that sequence, so you've got foam, 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 steel, foam, 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 and you try and compress that sequence, well, as you're squishing it from the side, it's not going to deform. You can apply huge amounts of force to it, but it doesn't deform because it's the layer of steel which is stopping the deformation. It's only when the layer of steel begins to deform that the layers of foam can deform as well. So when you're trying to deform a sequence of rocks, you have to overcome the strongest layer first. Now when we do deform a sequence of rocks, we will form one of three features: an anticline, a syncline, or a monocline. Now when we look at folds, folds can give us an idea of how much rock a stress has been exposed to and where that stress was coming from. So for instance, if we look at this diagram here, we can see here are the folds at the front. You can see that the rock is going up and down and up and down and up and down. It's been folded. Well, we can see when we look at the diagram, we can see the fold is orientated this way, isn't it? You can see the ridge produced by the fold. So the fold is orientated that way, at 90 degrees to the direction in which the rock is being squished. So the fold will always form at 90 degrees to the direction in which the rock is being compressed. And that's a very useful thing to know as a geologist, because that means if you start seeing folds in your rocks, well, that means you know the force that deformed that sequence of rocks must have been coming from essentially 90 degrees to that fold. So if we look at this diagram here, we can see two of these three features. We can see an anticline here. Anticlines essentially look like arches, so they come up and down. Whereas synclines, we can see here, naturally form troughs. Okay, so let's start by thinking about anticlines and synclines. So here's a couple of examples. So here's a nice anticline. You can see there's an anticline there. And here's a syncline here. Now, you're going to have to take my word for this one, but when it comes to anticlines and synclines, we need to think about where the oldest and youngest layers of rock are going to be located. So just imagine that the palm of my hand is the oldest layer of rock, and the back of my hand is going to be the youngest layer of rock, okay? And so my layer of rock is going to go like this, okay? So I've got the youngest on top and the oldest on the bottom. Now, as I begin to deform my rock to form an anticline, so I'm forming the arch, okay? In the middle of the anticline here, I'm going to have the oldest rock, aren't I? And on the outside, I'm going to have the youngest rock. So anticlines in their arch shape, an anticline has the oldest rock in its middle, in its core, and the youngest rock on the outside. Now let's think of a syncline. Well, in the case of a syncline, once again, oldest rock on the back, on the front of my hand, on the palm, youngest rock on the top. Now when the syncline begins to form, it starts to go down like this, doesn't it? So this means the youngest rock is going to be in the core of the syncline, and the oldest rock is going to be on the outside. So with this syncline here, this is going to be the youngest rock, and this rock out here is going to be the oldest rock. So depending on whether it's an anticline or syncline, we can predict with good accuracy where we're going to find the oldest and youngest rock. And that's very, very important, because that means when we look at maps of areas and we look at the rocks and we look at how they're deformed, we can see by working out, well, is it the oldest rock or the youngest rock in the middle of this feature? That helps us work out, is it an anticline or a syncline? Okay, now a few other features that we need to discuss. So in this case, we're going to have an anticline here. We're going to use that as part of our discussion. Okay, so an anticline has what's referred to as an axis. Okay, and an axis is an imaginary line that runs parallel to the ridge produced by the fold. Okay, so if I just go back for a second, the axis for this fold is going to come along the ridge right here. Okay, so that's going to be my axis. And you can see it here, it's marked out by this dashed line. Now, this axis will form what's referred to as an axial plane. An axial plane is a two-dimensional sheet. Okay. Now, the actual plane can move depending on how the fold is. If the fold is upright, then the actual plane is going to be upright. If the fold is tilted somehow, the actual plane will start to move. So the actual plane can rotate around, and we'll see that when we look at different types of fault later on. The final thing we need to think about is how these folds are represented on maps. So on a map, it's not uncommon to see a dashed line like this with arrows either coming away from the dashed line or towards the dashed line. Now, when you have a dashed line like this and arrows coming away from it, that means what you're looking at is an anticline. When you have a dashed line with arrows moving towards it, that means it's a syncline. So anticline, syncline. Anticline is an arch, syncline is a trough. Okay? So now don't get axis and actual plane mixed up. So remember, axis is just a single line. It's an imaginary line that runs parallel to essentially the ridge produced by the fold. And the actual plane is a two-dimensional sheet, essentially. And the actual plane can move around depending on whether the fold is upright or whether it's been tilted. And these diagrams here kind of give you an idea. So here's an anticline, and here's a syncline. Now you can see in both of these cases, the syncline and the anticline, when you look at the fold, it's perfectly upright, isn't it? So we can see, if we look at this diagram here, the axis of our actual plane is going to come along. So the axis of our anticline is going to come along here. The axis of our syncline is going to go along there. So everything good so far. And because these anticlines and synclines have not been tilted, they're perfectly upright, the axial plane will be a vertical sheet, like we can see here, this blue sheet. Now, if our folds have been tilted, however, so our folds aren't upright, they've been pushed sideways, well, what's going to happen? If we look at this picture here, this is a situation where our folds have been pushed sideways slightly, so they're leaning. Well, what do we have? Let's look at our axis to start with. Remember, the axis is the line. So if we look at the axis of our folds, well, the axis is still going to go along the surface like this and like this. Okay, so the axis for these folds here looks just like the axis for these two folds here. It's just going to go along the surface just like that. Nothing special. Looks exactly the same. However, because the fold has now been pushed sideways, the axial plane is no longer vertical, but the axial plane will be tilted. And so if the axial plane tells us that the fold has been pushed over, because if the fold is upright, the axial plane will be vertical. As soon as the fold starts to get pushed over, the axial plane will start to rotate along with the fold. And so that's what we're seeing in this picture here. You can see the axial planes picked out by these two blue sheets aren't vertical, they've been tilted. And you can see the same thing here on this diagram here. So this diagram shows you the four main types of fold. The first type of fold is what's called a symmetrical fold. In a symmetrical fold, the fold is upright, and each of the limbs, so the limb is one side of a fold, so you have one limb over here and the other limb over here. The limbs are the same length and they are the same angle. So essentially it's a symmetrical fold. Over here we have an asymmetrical fold. As you can see, the limbs are different lengths and they are different angles. You will also notice that the axial plane is no longer vertical, it's tilted slightly. So there's the axial plane. Then we have what's referred to as an overfold. As you can see, that's essentially a situation where the fold is being tilted even further. Now this fold has been tilted so far that one of the limbs is now nearly vertical. Well, it is vertical. And that's the classic definition of an overfold. If one of the limbs becomes vertical, or just before or just after vertical, that's going to be an overfold. The final type of fold is this type of fold, which is called a recumbent fold. And that's when the fold has literally fallen onto its side. So it's recumbent. Now the thing you will notice about a symmetrical fold, an asymmetrical fold and an overfold is if you look at the axial plane, They're all just lines on the surface, because the axial plane tells you nothing about how, which way the fold is leaning. Okay, it just tells you about the fold's orientation. It's only when you discuss the axial plane that you actually know which way the fold is leaning. Okay, I know that's a lot of information. I'm just trying to get it out now because we're going to cover it again and again and again. So hopefully by the end you'll have a pretty firm grip of the axis and the axial plane. Okay, so we're just going to have a look at these two slides and then we'll call it the end. Call an end to part 2. So we can see quite clearly here. This is a, well, you can work it out for yourself. What do you think? Anticline or syncline? 3, 2, 1. What's your answer? I'm going to guess you are probably mostly right. It's a syncline. So we can see the trough shape right here, can't we? We can see the layers of rock coming down and then coming back up on the other side. So they're coming down and up. So we have a trough. Okay, so that's a syncline. So this means that as it's a syncline, does that mean the oldest or the youngest layers of rock will be in the middle? Okay, so remember, here's our sequence of rocks. Youngest on top, oldest at bottom, and we're going to cause our rocks to fold downwards, to buckle downwards like that. Are we going to have the youngest or the oldest in the core of our syncline? The answer is youngest. So we're going to have the youngest rocks in the middle here, and the oldest layers of rocks are going to be here on the outside. Okay, now that's important for geologists to know, because that means we can work out essentially which way our sequence is going, so we can date our rocks correctly. The axial plane for our sequence is going to be coming up something like this. And you can see when you look at this syncline, when you look at it, it looks quite a nice symmetrical syncline. So we know our axial plane is going to be pretty much vertical. Okay, now let's look at a fold on a really big scale. So if we look here, this grey area here, these are the coal fields of South Wales. Wales is part of the United Kingdom. Okay, the coal fields of South Wales are very, very famous because they produce some of the best quality coal the world's ever seen. Produce a type of coal called anthracite, really good quality stuff. So the question is, well, how do we look at this map and how do we realise that we have a fold here? I've just got to scratch my knee, I do apologise. Okay, so the first thing is well, once again, we can see we've got one of these features where it's closing up. It kind of looks a little bit like that diagram we saw all the way back at the beginning of the Appalachians, doesn't it? We can see we've got one side of the fold coming this way, one side of the fold coming this way, and eventually, if it was there, we would see these two sides of the fold joining up there. Okay. Now, the question becomes is this an anticline or is this a syncline? Now remember, the key is anticlines have oldest rocks in the core, synclines have the youngest rocks in the core. So what we need to do is we need to work out where these rocks sit relative to each other. Now we are lucky in that this is a geologic map, so we have essentially a stratigraphic column over here, which puts the rocks in their order. So 27 is going to be the oldest rock, number 1 is going to be the youngest rock. So okay, let's try and find out where we sit in the sequence. Alright, so well, we have ourselves this very obvious orange layer. That's quite a bright colour. We're going to find ourselves in the sequence, and dunk, there we are, 23. Okay, so that's a Devonian with limestones. Okay, so then we have this kind of, I'm not sure what we describe that, blue-grey coloured rock or colour, and then there it is there. There's that blue-grey colour. Then we have grey, light grey, which is going to be this layer of rock here. And then we have dark grey, which is going to be this stuff here. And then we can see the same layers of rock repeated on the other side. So we have light grey, very thin layer of it right there. We have this kind of blue grey, there it is there. And we have the orange, there it is there. Because of course, once again, if you remember all the way back to the Appalachian picture, you'll know the same layers of rock occur again and again and again when a strata is folded. So the fact that we have the same rocks on this side and this side is also another indicator that things have been folded. So this is Devonian, okay, and these are going to be, well, the rocks here in gold, they're going to be Permian, so this is going to be Carboniferous. So let's think about our geologic timescale: Cambrian, Ordovician, Silurian, Devonian, Carboniferous. So these rocks are younger than these rocks. And so that means what we have here is a syncline, isn't it? Youngest rocks in the middle. So what we have here is a really big syncline. And so this is how we work out whether it's an anticline or a syncline. So there's the axis of our syncline, and of course we have the two arrows pointing together, and that would tell us it's a syncline. And the way we worked out it's a syncline is simply by looking at the stratigraphic column. Okay, everyone, so we will come back, we'll look at this picture in just a second because we've really run over time. So this is the end of part 2. Once again, pause the video, get up, have a walk around, glass of water, cup of tea, cup of coffee, whatever you want, and then come back for part 3.